Right, this video is part of the trigonometry section. This is basically about radians and how we use radians, including small angles, small angle approximations. What does it say? Use of radians for measuring angles gives the advantage that the length of the arc and the area of a sector become very simple. The whole circle is 2 pi radians. So if we look at this sector that we've got drawn here, and the angle that sort of defines it is theta. Now the whole circle would be 2 pi, half the circle would be pi, and therefore this bit would be essentially would be pi over 4. That would be that amount of pi being 3. So it's about 0.7 radians if we want it in numbers. We don't tend to deal that much in actual numbers sometimes, but we kind of deal quite a lot in sort of multiples of pi. Anyway, so what we've got here, so given that this angle, whatever the value is, it doesn't really matter, is in radians, then it gives us a nice easy way of calculating the length of the arc here, as that length is equal to the radius times the angle, and the area of the sector would be a half r squared theta. Kind of in a sense, when we measure things in radians, we've already multiplied by pi. That's really what it comes down to. But that's not an overhead that we have to face. So it's it's kind of quite useful. So if we take those formulas and sort of just double check back with a whole circle where theta is 2 pi, so that length there around the whole circle would be the circumference. So r theta would be r times 2 pi, or 2 pi r. Okay, that is exactly what we recognize it to be. And the area, again, this theta would be 2 pi, so we would have a half times r squared times 2 pi, which is pi r squared, which is so checks out. Right, so it is a convenient way, and in general, the more analytical kind of maths, you tend to be working in radians, really. It gives us a convenient way of approximating small angles as well, because if we look at this, we've got this small angle here, then sine theta, well, as the angle gets smaller and smaller, then this ratio sine theta becomes closer and closer to the value of theta. Sort of makes sense, doesn't it? Because the sine is this over this, the opposite over the hypotenuse, and as we get smaller and smaller and smaller, it's the value gets smaller and smaller and smaller as well. Same with tan theta. Doesn't quite work for cosine of theta, because obviously that is the adjacent over the hypotenuse. But we've got this this little approximation here. So well, we'll see how that works in a moment. So that's a kind of very brief introduction to the use of radians. Now let's have a look at this. So here's an example. Sector AOB is a sector of a circle, radius 6 centimeters. Chord AB is 8 centimeters long, so we can imagine that, can't we? And find the angle AOB in radians, giving your answer to 3 decimal places. Now, I should note that when we use our calculator, we, for anything that's involved in radians, we need to set the angle input. So if you go into the menu and setup, then you'll have to change that. If it's already in degrees, change it to radians. And you will notice at the top of your calculator there'll be there's a little d that changes to a little r. Okay, so so you'll need to do that. Right, find the angle AOB in radians, giving your answer to 3 decimal places. Well, we just draw half of that triangle there. We can see that this is a right angle triangle. We dropped a perpendicular, dropped it upwards, 4 and 6. So, and this angle is half, isn't it, of theta? So sine theta over 2 equals 4 over 6, giving us theta over 2 by the calculator equals this value here. And theta is twice of that, so which is 1.459 radians to 3 decimal places. That be 1.459. It's about half of it's half of pi, isn't it? So and if pi is 180, it'd be 90. So yeah, it kind of looks about right. It's not drawn to scale, but it's approximately correct. Okay, good enough to give us confidence in the answer anyway. Calculate the area of sector AOB. Okay, well, we'll just go back to our formula, which I've written down here, half r squared theta. So that's a half r squared, theta being the size of the angle in radians, of course. Just multiply that through, and that's going to give us 26.27 to 2 decimal places I've used there. And then part C, calculate the shaded area. The shaded area basically is going to be equal to the sector area minus the triangle area. So what is the triangle area? Half base times height. Yep. Okay, so that's a half times the base of 8. Right, okay, so we have to do a bit of Pythagoras here. So this length, this is the height of that triangle, is going to be the square root of 6 squared minus 4 squared. Okay, so that works out as 8 root 5. So the shaded area, therefore, is this 26.27 we've got for the sector minus this, gives us 8.38 square centimeters to 2 decimal places. That is the area of that. And these kind of geometry problems involving, or trigonometry problems involving sectors are very often associated with this this particular topic. I mean, you wouldn't have to kind of do B and C. You wouldn't really need to do it with radians, would you? But part A asks you to calculate it in radians. So really that kind of sets the whole question in radians. Right, okay, let's have a look at another example here. Now this is with small angle approximations. You're not going to get a question as simple as here's the angle, what's the sine? Here's the small angle, what's the sine? It's always going to be something a little bit more complicated like this. Show using a small angle approximation that sec of an angle, sec x, equals 2 divided by 2 minus x squared. Well, secant is 1 over cosine, isn't it? That's what I've written here. And then the cosine of a small angle x is going to be, remember it was 1 minus theta squared over 2. So we're using x here, 1 minus x squared over 2. So if we multiply, we put the denominator over a common denominator of 2 and then just manipulate that, we're going to get 2 divided by 2 minus x squared when x is small. So that is an approximation. So I really should have written my approximately equal signs here, but I'll take that for granted. Hence, find the first 2 terms of the binomial expansion for sec x. Well, if you haven't done the binomial expansion yet, then this might not mean anything to you, but we'll just run through it anyway. So if we look at this, we can write it as this 2 minus x squared to the power of -1. So it's going to be 2 times, right? In order to expand this, we need it in the form of 1. We need it in this form, 1 minus something in x here. So we're basically going to divide through by 2, which is multiplying by 2 to the power of -1. Conveniently, these, of course, cancel, leaving us with this. And yeah, so that's what we're looking at. And then if we expand that using the binomial expansion, then we're just looking at the first 2 terms. There's going to be this. So you're going to have to look at the video on the binomial expansion in order to understand that. In actual fact, it refers here to the binomial expansion. Personally, I'd refer that to as the binomial series. But hey ho. So if we look at the first 2 terms, that is basically what we get. Now, you'll need to do that to do part C, obviously, but it says using your binomial expansion, which is this. The point with this is that we're not interested in other terms because they're going to be higher powers of x. And if x is small, then the higher powers of x are going to be less and less significant. That's why we're only interested in this level of approximation. But we can actually use this now in order to approximate secant of 0.1 radians, because we just substitute 0.1 in there, or 0.1 squared is 0.01. So we evaluate that to 1.005. So that would be our approximation for the secant. Again, I should be using the approximately equal signs in here somewhere, but not to worry. Okay, so that's as much as I think we need to do. There'll be worked examples on this, but just to recap, it's convenient. Some of the trig problems that we get with sectors and triangles and things like that actually work out quite nicely. We've got these small angle approximations, and questions like these, actually, they're sort of gold dust, really, because you get decent marks and they're not really that complicated. So hopefully that has been helpful. I'll see you next time.